All right, we are in our last section of chapter 9. So last section of sequences, 9.4, using recursive rules with sequences. So what we have been using previously is what's called an explicit rule. Today we are talking about recursive rules, and we'll get into the definition of that in a second. But your learning target is to write and use recursively defined sequences. So you can write terms using recursive rules. You can write recursive rules. You can go back and forth between recursive and explicit, and you can use recursive to solve real-life problems. So far, we have talked about explicit rules. So there's an example there in your book. An explicit rule gives a sub n as a function of the term's position number n in the sequence. So as long as you have the position number, you can find the term. Another way that we can define a sequence is by using a recursive rule. A recursive rule tells you how a sequence occurs based on the preceding terms. So what happens between each term? This one is a little less efficient because just because you have the term number doesn't mean you can find the term. You're going to have to know the previous term to be able to find the next term. All right, so for our first section here, we're evaluating recursive rules. So we're just determining what the sequence is from the rule that they give us. So part A, write the first 6 terms of each sequence. Part A sub 0 equals 1. That means that my term before the sequence starts is 1. And I'm going to make a note right here that this, I'll put my arrow down here. This number is actually going to be the start of the sequence because that will be a sub 1. Okay, so if we start with 1, the next term, what this is saying is that a sub n equals a sub n minus 1 plus 4. So this term equals the previous term plus 4. So I'm adding 4 each time, which means that my next term there is 5. So my start of my sequence is at 5, and I'm going to write 6 terms from here. So I need 6 more. So I'm adding 4 each time. I got 9, plus 4 is 13, plus 4 is 17, plus 4 is 21. 4 is 25. So that is my answer, the first 6 terms. Be careful with that a sub 0. That is not the start of your sequence. All right, part B, function notation. F of 1 equals 1. That means my first term is 1. F of n equals 3 times f of n minus 1. So that means that each term equals 3 times the previous term. So if I want to find the next term, I'm multiplying by 3. So 1 times 3 is 3, times 3 is 9, times 3 is 27, times 3 is 81, times 3, hold on, is 243. I had a brain fart there. So this is my answer right here. Okay, try these 4 practice problems. Take just about 5 to 6 minutes. All right, number 1, you should have gotten your first term as 3, and each time you are subtracting 7. So 3 minus 7 is negative 4. Minus 7 is negative 11. Minus 7 is negative 18. Minus 7 is negative 25. Minus 7 is negative 32. All right, number 2. A sub 0 is 162, and each time we're multiplying by 0.5. So 162 times 0.5 is 81, And remember, if it says a sub 0, then my start of my sequence is right there at a sub 1. All right, 81 times 0.5 is 40.5. 40.5 times 0.5 is 20.25. Times 0.5 is 10.125. Times 0.5 is 5.0625. And then times 0.5 is 2.53125. That looks a little funky there, but that's your first 6 terms of that sequence. All right, number 3, again, f of 0 equals 1, so that's not my start. My start of my sequence is going to be the next number. But I'm noticing that this one's a little weird. This is saying that each term is my previous term plus the position that I'm in. So if I take my previous term 1 and I add, which I'll make a little table here to make it a little easier. So previous term is 1 plus n is 1 plus 1 is 2. Okay, position 2, previous term is 2 plus 2 is 4. Previous term is 4 plus 3 is 7. Previous term is 7 plus 4 is 11. Previous term is 11 plus 5 is 16. And then finally my 6th term, previous term is 16 plus 6 is 22. So that sequence is 2, 4, 7, 11, 16, 22. All right, and then last one, my first term is 4, and then I'm taking 2 times my previous term at minus 1. So 2 times 4 minus 1 is 7. And then 2 times 7 minus 1 is 13. 2 times 13 minus 1 is 25. 2 times 25 minus 1 is 49. And then 2 times 49 minus 1 is 97. And I'll write this right here so you can refer back to it. All right, number 5. Explain the difference between an explicit rule and a recursive rule. So like I said earlier, you should understand by now that an explicit rule can give, or we'll say find, can be used to find any term given its position in, while recursive rules rely on you knowing previous terms. All right, take just a couple more moments to copy these down. If you need to pause the video, you can pause the video here for everyone to finish writing. Okay, I'm gonna go ahead and move forward. So writing recursive rules, if we have a sequence and we wanna write a recursive rule, arithmetic is easy. You're just writing previous term plus the common difference. So remember, you might wanna make a note, previous term, the way we write that is a sub n minus 1. geometric sequence, you're taking your common ratio times your previous term. All right, so example 2. Part A, we have 3, 13, 23, 33, 43. First thing you want to write, what is your first term? A sub 1 equals 3. Then you're going to write your rule. So A sub n equals my previous term. And then what am I doing here? Well, it looks like I am adding 10 every time. So that is plus my common difference 10. All right, part B. This one is growing very rapidly, so you should be able to tell that that's geometric. So I'm going to take 40 divided by 16 to find my common ratio. And that's going to give me that it is 2.5. So my first term is 16. You always write your first term. And then my rule, A sub n equals my common ratio 2.5 times your previous term, A sub n minus 1. Okay, example 3. Again, writing a recursive rule. So these are a little different. They're not arithmetic or geometric. So we have to be able to determine what's going on. Well, if I want to think about it, I probably am using the position somehow. Or if I look, it looks like I'm adding the previous 2 terms. So 1 plus 1 is 2. 1 plus 2 is 3. And 3 plus 2 is 5. So how am I going to write that? Well, I'm going to say, again, first, my first term is A sub 1. And then I'm going to say A sub n equals, it looks like I am taking the previous 2 terms and adding them together. So I'm taking previous term, A sub n minus 1, plus the term before that. So A sub n minus 2, if you go back 2 positions. So I'll make a little note here. Previous term plus term before that. So that is my recursive rule there. Okay, for part B, this one's a little different. It looks like I'm multiplying maybe. So let's say 1 times 1. So I'm taking my number, my previous number, and multiplying by its position. And then multiplying by 2. And then multiplying by 3. And then multiplying by 4. So I'm taking, I have A sub 1 equals 1. And then A sub n equals, what I'm doing is I'm taking my previous term, A sub n minus 1, and I'm multiplying it by the position that it's in. So times n minus 1. So multiplying, I'll make a note here too so you can look back at this. Multiplying each previous term by its position. So A sub n minus 1 is the previous term times its position n minus 1. All right. Try these self-assessment problems. Take just 4 to 5 minutes. All right, number 6. You should have found that this is geometric and you're multiplying by 7. So A sub 1 is 2. A sub n equals that common ratio 7 times previous term A sub n minus 1. Number 7, you should have found that you are looking at an arithmetic sequence. You're adding 11 each time. So a sub 1 equals 11. And my rule is that I'm taking each previous term, a sub n minus 1, and I'm adding 11 to it. All right, number 8 is a little different because it is not arithmetic or geometric. We're not adding or multiplying the same thing every time. So we got to figure out what we're doing. And what it looks like I'm doing is I'm taking my two previous terms times each other. So 1 times 2 is 2, 2 times 2 is 4, 2 times 4 is 8, and then 4 times 8 is 32. So a sub 1 is 1, always start with your first term. And then a sub n, we're taking our previous two terms, a sub n minus 1, and multiplying it by the term before that, a sub n minus 2. All right, pause if you need to keep writing. Example 4, translating from explicit rules to recursive rules. So the first example, we've got explicit, a sub n equals negative 6 plus 8n, and recursive, oh, not B. We're just at part A, sorry. Goodness. So a sub n equals negative 6 plus 8n. What I'm going to do is I'm just going to fill in my table. And we don't have to go very far. So if I plug in 1 for n, my first term, I'm going to get negative 6 plus 8 times 1. And I'm going to find that my first term is 2. And then to find my second term, so I'm plugging in 2 for n, negative 6 plus 8 times 2. I'm going to get 10. Negative 6 plus 8 times 3, I'm going to get 18. And so I'm going to notice here that I am adding, did not mean to write 6, I am adding 8 each time, which you could have told from your explicit rule that it is arithmetic because it's a linear function. And my slope is 8. So to write a recursive rule, again, you write your first term, which we just found was 2. And then a sub n equals, arithmetic, we're taking our previous term, a sub n minus 1, and we're adding 8. So this is my recursive rule. Part B. Actually, geometric is a little easier because geometric literally gives you your first term and your common ratio. So if I want to write my recursive rule, I'm saying a sub 1 equals negative 3 because that's given to us. And then a sub n equals my common ratio, 1 over 2, times my previous term, a sub n minus 1. So with arithmetic, you're going to have to find the first term. It's not just explicitly given to you. With geometric, it's literally there given to you. All right, example 5, if we're going from recursive to explicit. If my first term is negative 5 and I am subtracting 2 each time, that means that a sub 1 equals negative 5. I guess I wouldn't need to write this again. But if I'm subtracting 2 each time, that means that I've got a common difference of negative 2. So my explicit rule is a sub n equals my first term, negative 5, plus n minus 1 times my common difference, negative 2. And then think back to when we did arithmetic sequences, we are going to simplify. So negative 5 minus 2n plus 2, and then combine like terms, negative 5 and positive 2, to get negative 3 minus 2n. All right, part B, a sub 1 is given to you, it's 10. And then a sub n equals 2 times a to the sub n minus 1. That is a geometric sequence, and that means that my common ratio, what I'm multiplying by each time, is 2. So I'll make a little note right here. This is arithmetic. And this is geometric, so we're using our formulas that we were given for each of those. All right, so a sub n equals first term 10 times common ratio 2 to the n minus 1 power. All right, I know I wrote that kind of quickly, so if you need to pause here, go ahead and pause so people can write. Okay, self-assessment. We're almost done. Self-assessment, go ahead and try 9 through 12. Take about 7 to 8 minutes. It might take a little longer on this one. All right. Numbers 9 and 10, you're finding the recursive rule. So you have to figure out what a sub 1 is. And then what are you doing to the previous term? So to find a sub 1, I'm going to plug in 1. So 17 minus 4 times 1. 17 minus 4, which is 13. And then if I am subtracting, if I have a slope of negative 4, that means that I am subtracting 4 each time. So I'm taking my previous term and I'm subtracting 4. All right, number 10. That's your a sub 1 and your r. So a sub 1 is 16. To find any term, you're taking 3 times the previous term. So a sub n equals 3 times a sub n minus 1. All right, going from recursive to explicit with numbers 11 and 12. Number 11, a sub 1 is negative 12. Common difference is 16. So a sub n equals negative 12 plus n minus 1 times my common difference, 16. And then we simplify. Negative 12 plus 16n minus 16. Combine like terms. A sub n equals negative 12 minus 16 is negative 28 plus 16n. All right, number 12, you should be able to tell that that is geometric. So a sub n equals your first term, 2, times your common ratio, negative 6, to the n minus 1 power. And please be sure you use parentheses around that ratio if it is negative. I don't know if I said that in the last video. But always, always, always use parentheses around a negative common ratio. All right, last problem for today. Solving a real life problem. Or last two problems, sorry. We got one for, I don't want to say that. Okay. Example 6, modeling real life. A lake initially contains 5,200 fish, so that's a sub 1. Each year, the population declines 30% due to fishing and other causes, so the lake is restocked with 400 fish. So we are going down by 30%, which means we are multiplying by 0.7. I'm taking 100% minus 30%, so I'm finding 70%. And then I'm adding 400. So a recursive rule, a sub 1 equals 5,200. And then each year, I'm taking the previous term times 0.7. So 0.7 times a to the n minus 1, or a sub n minus 1. I don't know why I keep saying that. Plus 400. Part B, find the number of fish at the start of the 5th year. So that's the unfortunate thing about the recursive rule. You have to keep going until you get to the 5th year. So I'm going to fill in a table. So my first year is 5,200. And then each year I'm taking 0.7 times that plus 400. So 0.7 times 5,200 is 3,640 plus 400 is 4,040. So that's at the 2nd year. Okay, at the 3rd year, I'm doing 0.7 times 4,040 and adding 400 to it. So that's 3,228. For the 4th year, I'm doing 0.7 times 3,228, and I'm adding 400 to it, so 2,659.6. And then at the start of the 5th year, I'm taking that times 0.7 and then adding 400. So 2,261.72. Obviously, if we're talking fish, we're going to round. And we're going to say 2,261 fish. I'm going to round down because we're going to have less than what the decimal says. All right, and then part C. So describe what happens to the population of fish over time. It's declining rapidly. I mean, like, even if you're adding 400, that can't make up for that decline. So declines rapidly with little help by adding 400. Something I want you to think about, if you want to pause and turn and talk to your partner next to you, will you ever run out of fish? Okay, so pause and talk about that for a second. All right, hopefully you would have determined that you would not run out of fish because you're at least adding 400. However, what happens when you go below 400? You're just gonna have a steady line, right? So if you keep adding 400, it's just gonna stay at 400 at some point. All right, example 7, modeling real life. A home buyer borrows $150,000 at 6% annual interest, compounded monthly for 30 years. The monthly payment is $899.33. Find the balance after the 3rd payment. All right, so this is my initial $150,000. 6% annual interest. So actually, let's skip example 7. Let's just not do example 7. I don't want to talk about this one right now. That'll make more sense when we get to exponential functions. Okay, so we're stopping there. That is 9.4, so that is all of chapter 9. Next class, you will do a little classwork assignment over everything, and then you will review. I am uploading the review key to Google Classroom, so please make sure when you go home after you do the review, you are checking the key so that you can ask Miss Whitwer any questions about that review. You can also email me, but there's no guarantee I will answer. So please make use of your resources. Talk to Miss Whitwer, talk to Miss Harris across the hall if you need to. They are all there to help you.